Hello, welcome back. So far we have learnt last few lectures on numerical approximations to parabolic PDE. So, today let us start another class of partial differential equations that is elliptic. Okay. So, as the title suggests, finite difference approximations to elliptic PDE is 1. So, that whatever following lectures I will put 2 and 3 depending on the topics. Okay. Now, when we say elliptic PDE, more general partial differential equations are Laplace equation. Okay. So, typical of this is completely depending on spatial coordinates, not on time variable. Okay. So, in this respect this is very unique, and the possible applications from which this originates, for example, potential flow and also magnetic conduction, electrical current, etcetera. Okay. So, let us see a bit of the Laplace equations origin and then proceed to numerical approximations. So, as I mentioned, for example, consider potential flow where the velocity satisfies irrotational. So, potential flow or irrotational, of course, there are some differences, but more or less from general point of view we can be written as gradient of a scalar if curl is 0. Then we have conservation of mass. So, if we combine this and this, we end up with, so which is a very popular Laplace equation. Okay. Similarly, we have in electricity or magnetism. So, we have del square B bar equal to 0, where this is a magnetic field and this is electric field. Okay. So, we can have several such examples. Okay. So, now what is the main feature of Laplace equation? So, consider Laplace equation, say del square u equals to 0 in some domain, then if it is 2D, okay, and 3D Cartesian, 2D Cartesian, so when we say this, here u is dependent variable x, y, z or independent variables, and there is no time involved in this. So, this is typical of general elliptic equations. Moreover, each with respect to each space, here we have second derivative. Okay. So, of course, you can have some non-homogeneous terms which we will see, but this is the simplest scenario, and these suggest that the domain of integration, of an elliptic equation is for example, in 2D this could be an area, okay, bounded by a closed curve C, whereas in 3D this is volume bounded by a closed surface S. So, this is the typical of elliptic equation. Okay. So, now let us see what are the possible boundary value problems. So, boundary value problems that are possible for Laplace equation is solve del square equals to 0 in omega u equals to some f on the boundary. So, this is the boundary of omega. So, I give one solve Laplacian in omega which is closed and bounded, then u equals to f which is known. So, that means the function is prescribed on the boundary. So, this is called, yes, you are right, Dirichlet problem. Okay. Then solve where the normal is given on the boundary, and this is, yes, again you are correct. So, this is Neumann problem. Okay. So, that means when you have a domain, you have function prescribed on the boundary. So, this is Dirichlet problem, normal prescribed on the boundary, Neumann problem. Okay. So, there is a third type as well. Some alpha times u plus beta times the normal is prescribed on the boundary. So, this is, some of you may not know, Robin problem. Okay. So, this is more general case. However, one note, for example, this is your omega, then so this is the boundary. Okay. So, if you want to prescribe part of it, say u equals to f here, whereas, so call this gamma 1, call this gamma 2 and g there. So, this is quite possible. So, that means u equals to f on gamma 1, g on gamma 2, where gamma is. So, this is very much possible. Okay. However, note 2 is very important. These two prescribing both u and the normal at a same point simultaneously is not possible, because we cannot satisfy simultaneously these two conditions. Okay. So, with respect to Dirichlet problem, okay. So, you have to solve del square u equals to 0 in omega, then say u equals to f on this, then the missing data is dou u dou n. Okay. Similarly, Norman problem, suppose, and this is G on this, then in this case the missing data is u. So, this has a name, the Cauchy data is u. So, this is Cauchy data. So, that means if, for example, here u equals to f, then here we need to determine, okay. So, suppose here G, then we need to determine, okay. So, this is the missing Cauchy data. Okay. So, now let us, so this is general motivation of Laplace equation and the corresponding boundary value problems. So, let us start with the corresponding finite difference schemes. Okay. So, since we have let us consider two dimensional case. So, we have second order derivatives in space with respect to both the variables. So, let us use a central difference scheme usual what we have been using. So, then let us see how the method proceeds. Okay. So, we consider Laplace equation 2D. So, this implies okay. So, now using central difference approximations for both of them, we get. So, you can recall u by delta x square plus equals to 0. So, where delta x is corresponding x grid length and this is corresponding y grid length. Okay. So, typically if equals to h, then 2 reduces to you can see if this is h square and this is h square. So, now we can combine. So, this h square is gone, then we have reduces to this term, this term, this term, this term, we have minus 2 and minus 2. Okay. So, this is the corresponding approximation, and this approximation, so I have to rewrite here. Okay. So, this is called standard five-point formula. Why? You can see. So, these are 5 points. So, I plus 1 j, I minus 1 j, I j plus 1, I j minus 1 and I j. So, this sits like this. Okay. Suppose this is I minus 1, I plus 1, j, j plus 1, j minus 1. Then we have, so this is u I j. Okay. So, then we have u I minus 1 j, u I plus 1 j, u I j plus 1, u I j minus 1. Okay. So, this is the structure of standard 5-point formula. Okay. So, you can see to compute the value here, it demands 4 values at these corners like this. Okay. So, now suppose you have further, the grid is proceeding, then when we ask for the value here, it asks for this value, this value, this value and the one next to it. Okay. So, we have to compute like that. So, let us see with an example, okay, how the standard 5-point formula works out. Okay. So, let us start an example. So, solve del square equals to 0 subject to u of okay, and say h is 5. So, let us see the grid first. So, the boundary x extends from 0 to 20 and h is 5. So, 5, 10, 15, 20. Okay. So, we make it so 0, 5, 10, 15, 20 and y is going from 0 to 10. So, this is our grid. Now, u of x 0 is 0. So, on y equal to 0 it is 0. So, here okay, then x equals to 10 is also 0, then u of 0 y whereas here it is u equals to 100. So, now what are the unknowns are, so we have grid points, so these are boundary points, okay. These are boundary points and these are the internal points. Okay. So, now we have to compute the value at these points. Okay. So, say we call them 1, 2, 3, right. So, now consider our discretization. So, this is minus 4 equal to 0. So, this is our discretization. So, now let us say this corresponds to 0.1. So, 0.1 corresponds to, so I 0, 1, 2, 3, 4 and j 0, 1, 2. Okay. So, this 0.1 corresponds to I 1 j 1, right. So, 0.2 corresponds to so all of them corresponds to j equals to 1. So, if we start writing this equation, okay. So, this equation u 2 1 u 0 1 u 1 2 u 1 0 1 equal to 0. So, at each of the points. So, P 1 P 2 okay. So, P 2 then this is u 3 1 plus u. So, this is I 2 and j 1 I 2, then this is okay and then 0.3. Okay. So, now out of this we have to use this data. So, for example, if you consider this u I 0 is 0, so accordingly this will be 0, this will be 0, this will be 0. Okay. So, we have to use that and then so use boundary conditions, say u of x 0 equals to 0 implies u I 0 equals to 0. So, for example, I will show you u of 0 y equals to 0 implies u 0 j equals to 0. Okay. So, when we substitute, what are the unknowns? The unknowns must be at these points. So, 1 1, 2 1, 3 1 must be the unknowns. So, this is an unknown. Okay. So, there are 3 unknowns. Okay. So, it is repeating 1 1, 2 1, 3 1. Okay. So, these unknowns can be solved using these boundary conditions. Okay. So, the whole crux of the problem is to solve this. So, now I am not solving the system, because we have to discuss few concepts before we do. So, I will just proceed further to explain those concepts before we attempt any specific example. Otherwise, at this stage you must understand, given the Laplace equation we discretize, which is standard 5-point formula, then we go for the discretization of the domain and identify the points which are to be solved, and then compute the corresponding discretized boundary values and run the system at each grid point, the internal grid points. So, then we get a system of equations, eliminate the boundary values and you get a system of equations in unknowns, and that needs to be solved. Okay. So far if you see the Laplace equation, it is homogeneous, there is nothing to the right hand side. So, the story remain the same even if we have something on the right hand side. Okay. So, let us see a case where we have right hand side non-zero. So, as you know, if right hand side, if you have a non-zero term, typically say it is also function of the spatial coordinates. So, then we say the corresponding equation is Poisson equation. Okay. So, having discussed Laplace equation, let us put Poisson equation and execute the discretization. Then when we realize both would lead to the same situation, which means we end up with a system of equations. So, then we can discuss the concepts involved, okay, in order to solve the system. Okay. So, let us now proceed to Poisson equation. So, x can be any point in a set in R n. So, this is more general. So, for example, 2D, so when I say x, if you want you can put some bar, okay, to distinguish. Okay. So, this means we are expecting what is this, right. So, example, say minus 20 for example. So, now if we go for 5-point formula, okay, if we go for 5-point formula, we get, say, with the h equals to half. So, then we get 1 over h square. So, h square will not get cancelled, okay. maybe I will discretize, then you understand. So, this means phi I plus 1 j by h square equals to minus 20. So, this would lead to we have 4 there, and that goes off. So, we get minus 4 phi I j equals minus 5. Okay. So, this is the corresponding discretized equation. So, now given the corresponding domain and the boundary, we do the similar process similar to the Laplace case. Okay. So, hence the net story is we end up with a system of equations even in this case as well. Okay. So, in either of the cases, let us look at the computations involved, okay, because now we have to focus on either Laplace equation, which we have discussed here, we end up with a system. So, either in this case or such Poisson equation. So, the main aim is we have to solve the system, and that involves some number of computations. Okay. So, now let us focus our attention to the computations. Okay. So, computations involved, right. So, if you consider our general equation, this must be I minus 1 I j minus 1 minus 4 equals to h square f I j. So, this is more general formula. So, make a pardon. So, this is I minus 1, okay, u I minus 1 j minus 1. Okay. So, this is where I j belongs to, it goes to n minus 1 cross. Okay. So, if you have a grid goes to n, so then what would happen? 1 to n minus 1, and similarly here. So, this is n minus 1. So, we have how many internal points? Internal points. Okay. So, one has to solve set of n minus 1 square linear equations. Okay. So, this is because I is varying from this and j is varying from 1 to n. Okay. So, the note is, so 1 any node, for example, if you take any node, it is asking for these 4 other nodes, right. So, any node has 4 neighbors contributing, and 4 neighbors are, so this and this, the distance is more than 1 step, and from here to here the distance is more than 1 step. Okay. So, any node has 4 neighbors contributing, hence the tridiagonal structure is lost. So, earlier case, if you recall parabolic etcetera, we used to have a simple structure where to compute a particular value you need a past few values explicit scheme. So, kind of. So, that suggests a tridiagonal system. However, in this case, so this is a deviation. 2, once you have a particular grid and internal nodes, we may expect need a method of arranging. I would not say arranging, it's like a counting, means from where we call 1, 2, 3 etcetera. Okay. So, you will be comfortable if we proceed further and see. So, for example, what I mean is as follows. So, for example, this is your grid, okay. Say further, and suppose this is your grid. And let us say this is the boundary. So, the boundary say this is the boundary, then these are the internal nodal points. Okay. So, now we have to obtain the solution at these nodal points. Okay. So, now how do we order them? Suppose somebody wants to run here, of course, we have original 1, 2, 3, 4, 5, and similarly for j. So, as usual we can have our own notation which we have been following. So, that is for I equals to 1 and j equals to 2, u I j is u 1 2. So, this is our usual notation. Okay. So, this is usual. So, but here we want to just make a convenient method, maybe we count it 1 2 3 4 5 6 like this, or so there are several possibilities. For example, you can count like this, you can count like this, okay, you can count like this. So, one typical method okay, this is one so which means, so for example, this point corresponds to 1 1, right. So, this corresponds to 1 1. So, here our n is 5. Okay. So, you will see this corresponds to I is 1 and j is 1. So, V 1 1 equals to V 1 plus, so 4 times 0 So, you may call it u 1 as well. Okay. So, this is our 1. So, now let us consider this point, I is 2, j is 1. So, u 2 1 will be V 2 plus 4 into 0. So, this can be u 2. So, that means we are, it is 1, 2, 3, 4, we are heading like this. Now, let us take this point. So, that corresponds to I 1 and j 2. Suppose I 1 and j 2. So, that will be u 1 2. So, V I plus 4 times 1. So, V 5. So, this can be u 5. So, that means this is our next point. So, then 6, 7, 8. So, this is just a simple enumeration. Okay. So, with respect to this enumeration, we get, so you consider this, okay, call it star, and you propose the corresponding enumeration, then star reduces to A v equals to f, where A has the following structure. And T and V okay. So, this is typically we are calling u 1. So, this is the general structure, but note, if you see the corresponding system, the system is sparse. Okay. So, if you have any system sparse, then definitely if you generally go for Gaussian elimination, then see when it is sparse, then a lot of 0 entries appear in the matrix. So, then when you try to solve using Gaussian elimination, it will produce at several intermediate stages, it will produce several non-zero entries. That means, it is not really making use of the fact that lot of 0 entries in the sparse system. Okay. So, we need to consider this factor and come up with some efficient solver. Okay. So, let us see to address this particular task. Okay. So, the next we try to think of addressing this. So, hence I am giving iterative methods. Okay. Iterative methods. So, a remark here, so what is the remark? sparse matrix is useful only when non-zero entries alone are required to store. I mean, this may sound I mean, I am not putting it like a book definition. When I say, see, having so many 0 entries, if you are still saving those 0 entries and then trying to meddle with it, then it is no longer useful, right. So, what I am trying to say is sparse matrix is useful when only the non-zero entries are handled. Okay. So, that is idea. So, for example, if consider a matrix so some matrix I am considering little large, so that we know the concept. Suppose this is the matrix A. So, you can see lot of 0 entries and we want to represent it, okay, so that only non-zero entries are handled. Okay. So, what are the possible methods? So, for example, we have 3 vectors A, B and R. So, where A is say non-zero elements, non-zero elements are given in A bar. Okay. How? This is 1.0, 2.1, then 2.0, then 0.5, 3.1, okay. Then so, this is vector A. What did we do? All that we have just stored non-zero entries. Then column index. So, what is the column index? Column index is, see, this is non-zero entry appears in which column? Second column. This appears in third column, this appears in first column. So, we just list that 2, 3, 1, 3, 4, 2, 3, 5, 4, 1, 2, 3. So, corresponding non-zero element in the corresponding column, this is the index. Then we have R bar. So, we have to define R bar properly. So, what we are going to store? What we are going to store in R bar? We are going to store in R bar, suppose how many non-zero rows, how many non-zero elements in each row. So, in first row 2 elements, in second row 3 elements. Okay. So, we could have put 2, 3, but we are storing slightly in a different way. Okay. So, consider r k plus 1 minus r k. So, the difference is giving 2 non-zero elements. Then here how many? 1, 2, 3. Okay. So, 3 non-zero. So, we have to show it as a difference. So, 5 must come here. Okay. Then similarly here how many? 1, 2, 3. So, we must have here 8. Then here how many? Only 1. So, 9, and here 2. So, 11, then 1. See, we want to have maintain the same dimension. So, that is the reason we are. So, what is the definition? The definition of r bar is elements in each row. Which elements? Non-zero elements in each row, okay, as so this means number of non-zero elements in each row as. So, you can see number of non-zero elements here 2. So, the difference of r 1 minus r 2 minus r 1. Okay. Then similarly here 3. So, r 3 minus r 2. Okay. So, this is an efficient way of storing, and then one can see all the non-zero entries are only handled. So, the 0 entries we did not. Okay. So, this is worth learning, because the crux of Laplace solving Laplace and Poisson equation reduces to solving system more effectively. So, we should know little bit of tricks how to solve the system. So, storing is one of the important parameter, important concern. So, we have learned this. Now, we proceed to the corresponding iterative methods in the next lectures. Until then, bye.